I'm James Song from the Adaptive Safety Design Group. Today I'm going to be talking about developing an automated method for parametric human modeling. Human size and shape have significant effects on human impact responses and injury risks. Conventional human models only represent occupants in a few sizes. Parametric human modeling, on the other hand, can account for the morphological variations in both skeleton and external body shape among the population. It can rapidly generate a large set of human models that can take into account for variations in diverse human geometries to improve safety equity in vehicles. In the summer, I attempted to develop an automated method specifically for mesh morphing. Mesh morphing is important because it allows human subject models to be represented by the same number of points in 3D point cloud structure, which is helpful for later statistical analysis. Current landmark-based mesh morphing largely depends on radial basis function. However, there are two limitations. It often associates with large regional errors that were not covered by landmarks, and template mesh mapping requires manual landmarking on each sampled subject, which is very time-consuming. To improve the method, I developed an automated mesh morphing method to map a template mesh onto the subject geometry. This method should create a geometrically more accurate mesh of each subject while having a good mesh quality. It should include a self-correction mechanism for large geometric errors and bad mesh quality. And it should also automate the landmarking process, which will make the whole mesh morphing process less time-consuming. Here's an overview of the method. In step 1, we use radial basis function with predetermined landmarks. This is the old method. In step 2, we use adaptive RBF. This is the bulk of the new method. Step 3 and step 4 regards regional inaccuracies in the morphed model. Adaptive RBF is characterized by its ability to place landmarks automatically. Landmarks are chosen at points with largest errors. Each point's error is calculated using KD-tree. After choosing the landmarks, we also have to make sure that the landmarks are far away from each other as well. Through experimentation, if landmarks are placed too close to each other, it would distort the mesh. Currently, it seems that 5 mm is a good measure, but distance controlling parameter is still something that can be changed. After finding the source landmark, the target landmark is placed at 1/10 the distance between the source landmark and their closest neighbor in the target point cloud. This includes all the previously placed target landmark, which means that landmark location changes every iteration actually. This is because with KD-tree nearest neighbor, we are never too sure that the nearest neighbor is the correct corresponding landmarks for the source landmarks. That's why we try to morph the model little by little. Another algorithm that we use is the Coherent point cloud registration algorithm. It does not use landmarks to calculate 3D placement fields, unlike RBF, which makes it very convenient. Instead, it treats point clouds as a whole. It is good to account for regional inaccuracies, especially near the coastal facet regions. Note that CPT can also be applied to vertebrates as a whole, but we should never forget that T-spine vertebrates have defining features that only the landmarking process can take into account. This is why CPD, when applied to vertebrates, results in suboptimal mesh quality. Another defining feature of the new method is the self-correction mechanism. For bad mesh quality, they are identified with the triangle quality formula. If the triangle is near an equilateral triangle, it is considered good mesh. Otherwise, if it's close to a straight line, it is considered a bad mesh. We replace the bad mesh by placing surrounding landmarks around it and match the corresponding original baseline mesh using RBF. This process is similarly applied to large regional inaccuracies, except this time we use points around the point with the largest errors as landmarks and remorph the surrounding mesh. The results are very apparent. In figure 4.1, we can see that the root mean square error for the new method on all 94 subjects are all below 1 mm in error. In figure 4.2, there's a clear improvement in the maximum error when we compare the adaptive RBF plus CBT method with the RBF method. There's a huge decrease in the maximum error, which means that regional inaccuracies are taken care of. There are still visible regional inaccuracies, especially around the coastal facet area for the RBF method, but there are none in the new method. In conclusion, the newly developed adaptive mesh morphing method has increased geometric accuracy by a lot, and the remorphing method was integrated to correct the rare large geometric errors or low quality mesh after initial adaptive mesh morphing. It can automate the landmark placement process smoothly right now, so in future, the work should be focusing on reducing the manual landmarks from 19 to 4. Thank you.